Hello class, so I'm finally going to do some intro. I'm going to magnetism, specifically from a wire. I am going to be putting up definitions for you to copy down as well as talk about them. So your goals out of this is to have a better basic understanding of magnetism and how it works, as well as how a current forms the magnetic field, and solving an equation with Amperes Law. So first off is definitions. If you're not sure where you might want to write this, a good place might be your packet on page 2. So first off, excuse me, it's the electric field. So remember, the electric field is symbolized by B. The unit is the Tesla, or T. It's whether you have a magnetic material or a moving electric charge where a magnetic force acts on it. So you can either get a magnetic field from some sort of magnetic material, which is where you'd find your regular bar magnets, or if you have an electric charge or electric current on a wire moving. Alright, so magnetic force is that force that's felt by a magnetized object. Its symbol is FB. And remember, it's still a force, so your unit is still newtons. So it's the force felt by a magnetized object in a magnetic field, so that magnetized object could be magnetized material, or again, remember, a moving charge will act as a magnetized object. 3, magnetic flux is the amount of magnetic field moving through a surface. That's when we change our magnetic field. Remember, that's how we got our lights to light, by moving the magnetic field. So, and that's Faraday's law. Faraday's law is the magnetic flux, or a change in the magnetic field, will create a voltage in a circuit. It is also signified by this formula, where V, you remember voltage, is equal to the change in magnetic flux, or the change in the magnetic field, over change in time. So that tells us that if we have some magnetic flux over some amount of time, we can create a voltage. This is how generators work. 5, Amperes Law is the idea that, remember in our lab, we saw that if we have a circulating or moving current, we will cause a magnetic field. And this is shown by the formula. The magnetic field times, and actually, this is not the way I want you to write it. It is better written and easier for you guys if you go 2 pi r. So this was how you might measure the cylindrical over wire, the cylinder, but just go ahead and do the magnetic field times 2 pi r is equal to the mu naught times I, the current. So that's the idea that some current times a constant, this is just some number, it's a large number, I'm not going to write it right now, it's on the board, is equal to the magnetic field times the 2 pi radius from the distance of the current. Alright, and then you have a north and south pole to every magnet. This is called a dipole. Magnets are dipoles, so you cannot have a magnet with only one pole. There's always a north and a south side, and your magnetic field lines always connect. So remember, when we had a positive charge, these field lines could go out, they don't go anywhere. With a magnet, there is always a place that they are going to go. Alright, right-hand rule, remember, that is the rule to determine the direction of your magnetic field, current, charge, and force. The fingers are your magnetic field, B. Your thumb is the current charge, either that is the current direction or the velocity of one moving current. And then your palm is the force if it's positive, and the force backhand if it is negative. We're not going to really get into the mass spectrometer on here. If you want to know more about a mass spectrometer, come and talk to me. Alright, so imagine that we have two wires. Let's just call this wire A and wire B. So wire A is coming out towards you. Wire B is the current is going into the page. And so these each create a magnetic current. So to figure this out, you still want your thumb to follow the direction of the current. So in A, if you can visualize it, your thumb would be pointing into the screen. For A, your thumb would be pointing out of the screen. For B, your thumb would be pointing into the screen. And then you curl your fingers out. So I'm going to try to draw this. You're going to have your thumb, your hand, and then your thumb is going to point this direction, and your fingers are going to curl in this direction. So you can see if you curl them, you're causing your fingers to go in this direction. So now that I realize when I drew that, I just drew a left hand. So again, be careful. Always make sure you do your right hand, because I was looking at my left hand while I was drawing the right hand rule. So again, your thumb would be coming out. If it's a right hand though, you'll notice your fingers are going to go across in this direction, causing your current. This would make your magnetic field circle around. On the other side, if you look at your right hand with your thumb pointing in, you would have your fingers curve around this side, and your thumb would point in that direction, causing your magnetic field, to curve around this. So either way, on a wire, you're going to have a curved magnetic field, but it depends on which way it's going. So according to this blue one right here, your magnetic field is up, but if you're on the other side, or it'd be down on the blue side and up on the green, whereas if it's going the other way, on the green side, it's going to look like the magnetic field is pointing down, and on the left side, or the blue side, it would be going up. So you can see how pretty much all they are is in reverse of each other, and these fields can interact with each other. Obviously, the further out you get, the weaker your fields get. And this is all based on Amperes Law, which we'll do a practice problem for in a moment. So let's say we had some current carrying wire going to the right, and we want to know what the magnetic field is at this point, are away from your current. So you have to think, what is that going to look like? So remember, point your thumb in the direction of the current and curl your fingers around. If you'll do that, you'll notice it should be coming up on this side, going around, and then going back. So at this point right here, it's going to feel a out. So if you can imagine, this is out of the page. So right at that point, it's going to feel a field that is outward. And then when you're solving it, we would want to use the equation B, 2 pi r is equal to mu naught over I, or times I. But we are solving for B, so we can divide 2 pi r both sides to get B is equal to mu naught I over 2 pi r. Remember, B is your magnetic field. Measured in Teslas. Mu is just a number, which is 4 pi times 10 to the negative 7th, just a number. I is your current, measured in amps. and R is your radius. That is measured in meters. Alright, first step is always to read the question. So a wire has a total of 0.2 amps going east. What will be the direction and size of the magnetic field 0.5 meters south? So first off, you should probably always draw a picture so you have an idea. So remember, never eat soggy waffles. So we have some current going east. So remember, if you want the magnetic field, point your thumb in that direction. And then we want to know what's happening here. 0.5 meters south. So we want to know what is the magnetic field at this point. So you do want to draw your magnetic field line. So remember, you want your thumb to follow along and then curve your fingers over. So if you do that, you're going to see that your magnetic field at this point, it would be just as it starts to curve back in. So your magnetic point would be in, and then you need to solve so that is your direction, and then you want to go and solve the size or magnitude of the magnetic field. So you're looking for a number. So this is where we would use Amperes Law, which is B2 pi r is equal to mu naught I. We are solving for B, so you should change your equation so that it solves directly for B. And really at this point all you need to do is plug in some numbers. Mu, remember, was just a number, which was 4 pi times 10 to the negative 7. Your current in this case is 0.2 amps. And 2 is just a number, pi is just a number, and R was 0.5 meters. Make sure you do double parentheses on the bottom when you divide to avoid accidentally multiplying, and solve. Small thing some of you may have noticed. Oh look, there's a pi on top and bottom. You can cancel it out to help make your lives easier. If you did this, you would notice that we get 8 times 10 to the negative 8. Oh, that looks like 18. I apologize. Times 10 to the negative 8. And that, remember, that is n. Alright, so hopefully you come in with a better understanding tomorrow, and we will continue to work on this. As always, if you are not yet ready to present, please be prepared to present tomorrow.